So you're going through here, and right. So firstly, Alice set up the contract and constructed an instance and made an offer, right? Sent that offer to Bob. And then Bob went and, we make sure Bob is responding. If Bob has no messages, we keep going. If Bob accepts, then we're going to pull out the instance of the contract that he actually had to propagate forward to continue to accept from the output script that he actually, provided for that particular output of that transaction.
Yep.
And then we go and look and we check what number that Bob revealed that he wants to pick in this, right?
Yep.
And if Alice won, meaning if these numbers are the same, then Alice is going to create this win script, which we just went through. How that's done, of course, it's done by the use of, first we set up a transaction, we do our sig hash, we actually sign the pre-image, and then we go and we actually provide, we set up who this contract is going to, and then we say, here's the signature from Alice, here's the nonce that Alice is revealing to be correct, and then here is the number that Alice picked. So that's how we get the win script. And then after that, we go and we actually create a Bitcoin transaction for Alice, which has an input from the acceptance transaction, redeeming it back to herself, in which the envelope is provided all the SPV data, and then the outputs to redeem is output 0 with this particular unlocking script, which frees those coins, allowing Alice to win. Right. Otherwise, if their numbers are not the same, they win. Right. And then you're done. And so if either way, because Alice is going to be honorable regardless of whether she won, she has integrity, right? She's going to fall through and say, all right, now we're done with this if statement. She's going to come down to afterwards, and she's going to send a message to Bob with her nonce, whatever it was, and her number. That's it. She's not going to say whether she won or whether Bob won. Why would she say whether she won or whether Bob won?
The script determines that.
Right, so Bob doesn't want to trust whatever Alice says. Bob's going to say, I'm going to see whether this works or not. I'm going to verify it. And then but that's all, right? And then we're going to basically return whether you win or whether they win. Back to the person who called this create challenge function all the way back at the very, very beginning at the top, right? All the way up here, right? And that is the create challenge function.
Nice.
Right.
That's how Alice works. That's how Alice plays this game. Right?
Yeah.
And then I guess there's one final detail, which is we either return that from this for loop. So it's in this for loop, and then there's a return statement in this for loop, which is on line 185. Or, we break out of this for loop, we step down, eventually the for loop breaks out of itself, it falls through, something didn't work, and we either rejected because we expired or something else happened. We got no messages from Bob, something else. This for loop is done. And that's what I said earlier yesterday. And then we kind of run into here. We say, okay, well now, Bob is not responding to my offer, so I want my money back. So how we do that is we say, all right, let's get the unlocking script. And we'll just run through this very quickly because we did it yesterday. We just say, here's the transaction. It has an input from Alice's original offer, the offer TX output 0, the script and the number of Satoshis that Alice had on offer. She's signing with none, and anyone can pay once again. She creates a signature using the pre-image, which is derived from the transaction, the hash type, the input index, the script, and the number of Satoshis, right? That signature is computed by the SDK. There is type coercion to get the signature into the correct type. Don't forget to add your sig hash type to your signature.
Right.
Don't. And then we set through the contracts too, and then we actually cancel the offer with the signature from Alice.
And she gets her money back.
Then we reclaim the money using the offer TX ID, SPV information, and the associated unlocking script, returning the money back to Alice because of this reason. That is the true end of that function. Now it's done, and then we return why the function or why the offer was rejected.
Yeah.
Why it didn't work. So now we've collapsed down this function entirely. That is how Alice plays this game entirely. In completeness.
Yep.
Bob! Not you, Bob, but actually the theoretical Bob. Bob would like to check for challenges sometimes. He long polls. He every 5 seconds is going to say, "Oh, do I have any new challenges from anyone?" Right? So Bob is gonna list all of the messages in his challenge inbox when this happens, and it's going to return a list of incoming challenges, which, as we can see up here, are subject to this interface. They have these things on them. So we get that list of messages, and then we're going to map through all of them, and we're going to coerce each one into this type. So to do that, we basically just go grab the message body. We make sure that the transaction will parse itself properly. We make an instance of the contract. Now, why are we making an instance of the challenge contract? It's for one reason and one reason only.
So that when
Bob looks at the contract,
he knows what he's agreeing.
He knows what the expiry is. Remember, you asked Braden originally, well, why don't we do this on chain? It's because Bob needs to do it himself.
Yeah, because it's peer-to-peer.
It's only for Bob to consider the offer. So 275, Bob does pull out that value from whatever Alice is offering when we list all the challenges that Bob might be able to make, right?
Yeah.
So it's pulled out. And that's what this function does. That's all this function does.
Yeah.
So that's something that Bob can do. He can list challenges from Alice, right? Show them on the screen somehow, right? That's it.
Yep.
Okay, so we're done with that one. Forget that. Bob can accept a challenge.
Mm-hmm.
So, when Bob accepts a challenge, there are two possible outcomes. Of course, we can see it here.
Mm-hmm.
Right? Either Bob wins or Alice wins. So, from Bob's perspective, he's accepting a challenge, which is from this thing that he just got one of when he lists. And he passes it in, and either he wins or he loses. That's all Bob does in this game. And I think this is probably the last function. There's a reject as well. So if Bob wants to, let's just do reject first because it's way faster.
Yeah.
If Bob wants to reject a challenge, it takes an incoming challenge. It acknowledges the message, making sure that he doesn't see the same message in his list again. And then he just lets Alice know, hey, I'm rejecting this message, this challenge with this TXID. Braden, based on the recent change that you made to Tokenator, why would I have included line 540 in this message body? Why include the TXID of a rejected challenge?
Because it changes the message, and each of the message IDs are unique to the message.
And it's totally not like I ran up against this error or anything. No, of course not. It's documentation.
So what was the problem? What was it doing before?
Messages must be unique when they are sent via Tokenator.
Oh, okay.
Every message must be unique.
Right.
Kind of makes it more explicit, though. This is what I'm rejecting, so it's probably good.
Yeah, that way you can explicitly reject a particular.
And we got some helper functions down here, which I just window hacked. This is not very good. It's like, okay, if I want to reject the latest challenge message, well, then I can do it like this. If I'm Bob.
Mm.
And if I'm Bob, if I want to accept the most recent one, I can do it like this. Right?
Right.
So that's rejecting. Right? Now we understand rejection. And we can move on. Once you know what it's like to be rejected, a few times maybe you'll have more success romantically. But only no, I'm joking. So now we can move to acceptance. So what if we get accepted? Then either you can win or you can lose. Or they can win. That's a pretty
you win, they win.
It's a pretty cynical view of of that, but yes, in this game, either you can win or they can win, right? So
you can never lose.
Well,
one
someone's
of them.
gonna win.
Yeah.
You could say heads I win, tails you lose.
Yeah.
But that's not how this works, because now we can do it in a provably fair manner using the blockchain. And there's some Freudian thing about how this is all because of my own insecurity, and that's why I would spend so much time creating such a robust contract for this. Somewhere in there. Right. But let's move on from that.
Yeah.
We don't want to think about that too long, do we? So we receive the offer transaction that we want to accept.
Yeah.
So we make the transaction, we parse out the raw TX from the message.
Mm-hmm.
Right? How is Bob going to play this game? Bob is going to take the offer script from Alice, which is this from the first output, and he is going to make a new instance of the contract from the
Locking
script.
Right.
And now, we're making a mock instance as well, and we'll get to this later. We need to do this because we need to know what the output is going to look like for the output that we must include, right? When we sign,
Is that standard?
remember that sighash single is included in this particular one, right? So when Bob accepts an offer on line 65, sighash single. So it's a little different, right? This is going to be more advanced than what we were doing before. All the other times we signed, we had to sign sighash none, but this time we're actually having to sign sighash single. So that's important. So Bob needs to provide a signature, and he needs to provide his number that he picks. So he's going to pick a random number because he doesn't know Alice's number at this point, not initially anyways.
Yeah.
Right? So he's got to do that. So anyways, what we're going to do is we're going to create an instance of the contract. And we're also going to create a mock instance, which is identical. In fact, if I highlight this, it should show the same thing. But yeah, I'm making this from the same locking script, basically. From the offer script, right?
Yeah.
Bob is going to pick a random number here. And by line 292, Bob does not know Alice's number at this point. If Bob knew which number, if he only knew, if only he could somehow tell, which he cannot, but if only he could somehow tell whether Alice picked 1 or 0 by this point, he could cheat.
Yeah. Oh, yeah.
And yes, he can't do that because he does not know. Now, if Bob knew how Alice was generating random numbers, he could cheat, couldn't he? If he knew anything about that process, that Alice used that secret process to generate random numbers, but he doesn't. So he then, right? We're using the helper on the mock. So the mock instance is having that helper called transform state, right? So think of this: we invoke the transform state. The transform state function on the mock instance using the random number that Bob is now going to go with. He's like, well, I guess I'll use this one, right? Call transform state, pass in the number. What that does on the mock instance is it simply mutates the state. Still needs the method decorator, even though it's not a public method. Always needs method decorator, even if not public method in a script.
So you can still call it even though it's private?
Well, yeah, because I'm not using get unlocking script. I'm not on chain.
No.
I'm off chain. I'm using a mock, right? Okay. So why would I need to do this, right? Why do you think we are doing this?
Because we transition to the next state.
Well, we transition to the next state, but why? Well, I'm in a mock instance. I'm not doing this in the real one I'm going to use.
Because you're
what information do I need?
You need to create your locking script.
Yeah.
Right. I need to create my next output.
Yeah. You've got to do the same
So first, we use the mock instance to transition the state to decide what will this contract be like after I reveal my number, right?
Well, not.
And then I know what that output will need to be in order for it to actually be that way when I sign. And then we say, all right, well, here's the next output script. It's just from that, right? So in summary, what is the function of the mock instance? Why do we need 2? Why can't we just use 1?
Because you're actually changing. You don't want to change your original one. You need to change your mock one.
Because what happens if you try to sign the script of the one that you changed and it's the new script that's already been updated? Will your signature work when you sign? Let's look at the pre-image, right? We already know the answer to this.
Yeah.
Is it okay to change number 5? Will your thing unlock still?
No, it won't.
Of course not. And how long did it take me to figure that out? Quite a long time. So yeah, you need to make a new one for the purposes of forecasting in the future, like in theory, in a theoretical scenario in which the state was updated.
Right.
What might my output script actually look like?
Okay. And that wasn't in the sCrypt. Yeah, that wasn't in the sCrypt documentation clearly stated then.
It was. No, and you know why not? Because they're using a lot of abstractions on top of this.
Yeah. Okay.
We are learning how to do this at the low level.
Yes.
We are doing the entire understanding of this, and that is good.
Mm.
There needs to be more people in the world who have a complete understanding of how this works from the lowest levels up.
Yeah.
And now you guys are some of those people.
Mm-hmm.
Oh.
That's important. Right. So anyways, we can now forecast out. That's the purpose of the mock, is to actually go and say, well, what might this be like if this state was incremented?
Mm.
You know, that's why in the counter contract, which is the only clue I got, it's called on-chain increment. Right?
Mm.
Why? There's increment, and then there's increment on-chain.
Right.
It's because one of them is called off-chain to forecast out what that script will be like for the purposes of signing. And one of them is a public method, and one of them is non-public. 34? Not public. Line 20, public. Now,
yes.
So in your public methods, whenever you have something that modifies a state like that, you should have a private version.
You should, because you can actually invoke it off-chain when you need to forecast out what your scripts will be like.
Yes.
That is how that works.
Mm.
Right. And I did not choose to call my private method in my public method. I chose to just do it explicitly and copy this code, literally, same code, 2 places.
Yeah.
But I couldn't actually get this to work. Maybe there's a way of doing it, but I think that we should just be explicit and just put it directly.
Right.
That's just the way that I found that it works. You can mess around and prove me wrong. But till then, this is the way that I'm going to do it.
Okay.
We've got this. I could have, like I said, 73, 74, right? I could have done that by calling that. I don't know if that would work. I don't think it would. Maybe we could try, but I'm not going to do it right now.
Yeah.
I can't bring myself to it because I don't think it would work. But that's just, maybe it would. I don't know. Right. Anyways. Bob wants to reveal, so he sets all this stuff up, right? He picks his number, he forecasts out what script he's going to need, and then he's like, okay, now I'm going to make an unlocking script to accept this offer. How do I accept this? And he assigns scash single and scash anyone can pay, right?
Mm.
So once again, get unlocking script method is invoked. It takes the self, which is an instance of the contract, and it's got to call a public method, and set the 2 value, right? So you set the 2, and you invoke a public method in the callback. Can be async. You should probably, you want it to await. You want it to be async.
Yeah.
So make a transaction.
Yes.
It's a little bit different, though, isn't it? Right? It's got to be a transaction with an output on it too.
Oh. Okay.
Who's the transaction from? Well, the TXID of the challenge transaction, right?
Right.
Output number 0.
Yeah.
Offer script 2x. Now, think about what would be true if I would have not used a mock instance. Would that have changed?
Yes.
I mean, well, not in this case.
Well, I see. If you had to use the offer.
Offer script comes from before I would have changed it on 285, right?
Yeah.
So that might not have changed. That would be okay, but let's keep going. Satoshi's, that would have been fine, right? But then we have to add an output, and we got to add the next output script, right? So here's where we're actually adding an output. Let's keep going. Adding an output to the transaction. We'll come back to that changing thing, so don't worry about it too much. Adding an output to the new transaction, which is twice as much as the one that we had before.
Right.
We're doubling the money.
Yeah.
And saying, here's what I'm signing. And I'm signing with this script on that output. That's the next one that we had to compute, right? We had to pre-compute that script.
Mm-hmm.
And we're saying, well, it must be single. It must be anyone can pay.
Yeah.
And for credit. Now, single is fine because it's the first output, and this is the first input.
Yeah.
Right?
So it's
So as
directly
long
across.
as the Savage creates this transaction later, it's also still the first output and the first input, then single still works, which is cool.
Hmm.
This is the first time we've ever used Zcash single in a Project Babbage context.
Hmm.
So off that went. We're signing with the pre-image, which comes from the transaction, with that input and that output on it. Zcash type of single, anyone can pay. Input index 0. And the script. Now, offer script, once again, I put here. This is the script that I'm signing. So that would actually be okay.
Hmm.
But for some reason, I couldn't get that to work, so that's why, honestly. I don't know exactly why that didn't happen, but I think mocking it is the way to do it.
Hmm.
Because if you mutate it, right? Actually, I figured out, it's because if you call this function and the state is not yet mutated, then it will work. But if it has already been mutated, then when this function goes to execute, it will not succeed.
Hmm.
So anyway, we compute the signature, coerce the types. Do I have to say it again? Yes, of course I have to say it again.
Yes,
Don't forget to add Zcash type to your signature after you create your signature. Set your transaction to. I don't know if this transaction.from is necessary, but tell who your contract is being spent by. Sometimes that's necessary.
Hmm.
Right? It was spent by the offer TX output index of 0. That's where it came from, where it was going to. And then we say, all right, have some conlogs in here. But there's the signature from Bob. And here's the Bob's number that he's revealing, right?
Mm-hmm.
So now Bob has successfully created this unlocking script, right?
Right.
Yeah.
And so now Bob has unlocked the acceptance transaction. We already talked about this, right?
Yeah.
You consume the input, create a new output. If Bob didn't do this part, and he just said, oh, I just want this money from Alice, and I'm just going to spend that, right? Wouldn't be valid.
Nope.
Blocking.
Only way that spend is valid is if this is also here. We already know what we agreed to.
Yeah.
Here's the next output script, and that's what it is. Put it in the basket just for making sure we keep track of it. We're not actually using the baskets for anything yet, but we can add that later. Here's the amount times 2 for the synergies, and that's it. Description, accept a coin flip bet.
Yep.
Right, there's the accept TX done. Right. All right. Now we acknowledge the message that came from Alice saying, yes, you challenged me, and I don't want to see it again. Then we send Alice a message, and we say, we're sending back to whoever sent that challenge. We're saying, all right, here's the response. Here's the action. I'm accepting the challenge, and here's the acceptance transaction. Right? And now, of course, you'll remember, so we're 371, we're sending this out, right? You'll remember that if we go back to the perspective of Alice and create challenge, that Alice is looking for that exact message in this for loop.
Yeah.
Alice is saying, look, do I have a message that has an action of accept? And it's got an accept TX in it. And if so, do the numbers match? Do I win or do I not win? Right? And either way, after I do all of this, after I sign, maybe if I won, I'm going to reveal to Bob my hand. I'm going to say, here's what I have. I have a number and I have a nonce. Right. So Alice gets back to Bob. Now we're back down to where we were on 370 something. We acknowledge that and we sent that off.
Yep.
What do we expect back from Alice?
Yep.
We literally just saw the code, right?
Yep.
While true. Oh no. But, right, waiting for Alice for 5 seconds. We'll give her 5 seconds to respond. Let's see if the current time is more than the challenge expiry time plus 5 seconds. If the challenge has expired plus 5 seconds, they're going to break out of this loop. And what happens when we break out of the loop? Well, that happens all the way down here, and we'll get to there on 470 later.
Yeah.
It'll be the very end of this function, in this file. And probably this day.
Yes. And us.
we go and list the messages from Alice. We see if Alice sent us anything. If she did not, then we keep flipping again until the timeout has expired. So Alice has until the timeout has expired plus 5 seconds as a grace period to respond. So we grab messages from Alice. We see if there's any messages. And finally, we pull back something from Alice if she has sent us something.
Right. Now, does Alice actually correspond manually, or can it be done automatically?
So it's done using that code above.
Yeah.
Right.
On Alice's side. On Alice's
side is going to pull and wait for Bob to accept, and once he does accept, Alice will reveal.
Yes, but you said she could actually not reveal, so it must be manually.
You're right, but only if Alice had malicious code installed on her.
Oh, okay, yeah.
Alice was in fact running a hacked plan, or Alice wanted to be fancy and just fool people.
Oh, right.
She'd go into her client-side code and be
CoinFlip plus.
Right.
So when these messages are sent via peer mail, is it actually manually interacted with? Or I suppose the acceptances, I mean, each side has to, Alice or Bob has to.
For acceptance
is
that Bob lists any incoming challenges and clicks the little green check mark to accept the challenge.
And that is the only manual intervention. Right, got it.
Right. That's why we list accept and reject.
Yeah.
Otherwise, it could be automatically accepting, but if I automatically challenge people, that would be a little bit.
Yeah. You could perhaps let your agent to do it, but maybe not.
All right. You could code that up if you wanted.
Yes.
You're in charge of your own coins.
Yes.
Side.
Yeah, agreed.
So Alice gets a message back. Bob has now received a message back from Alice, assuming Alice is honest. Because remember, if we're beyond 5 seconds of the grace period that Alice has to respond, then we're just going to break.
Yeah.
We're going to be out of here. We're going to fall through and try to just take the coins using the backup method. But supposing Alice is honest and she does respond, then we pull that out and we say, okay, here's what you said.
Yeah. So actually, you mean, if Alice's code is honest, that's what you mean, not even Alice.
Right. Now, Bob is going to authenticate the nonce and the number that Alice revealed. Right? So Bob is going to make an instance of the contract that he himself just accepted. We're going to make a new instance of the contract that he himself already accepted. The revelation instance, he's going to call it. And it's going to create a hash. He's going to create a hash for verification from the Alice's nonce.
Yeah.
And the Alice's number.
Right.
Bob is going to just check what Alice said, and if the hash for verification is not equal to whatever was in the contract, right?
Yeah.
Then Alice lied.
Yeah.
And if Alice lied, then guess what? We continue. And I keep expecting either until the timeout passes or until Alice decides to come back, be honest, and tell the truth. Those are her choices.
Or rather, her code does.
Alice could send 2 messages first. First one being false, and then finally get to the truth and noting the still work.
Yeah.
Up until the expire date. Yeah.
Up until the expiry. She has until the expiry date to let her conscience be. At which point, maybe the guilt would overcome her at the last second. And then,
in fact, you should get Bob to be sending Bob's code to be sending messages. Are you sure?
Right. And you get AI agents involved.
Yes.
That would be crazy.
Yeah.
Right. So if Bob does not receive a truthful response from Alice, he just disregards it silently. For the time being.
Yeah.
Now we know that is actually correct. We know that Alice's number and her nonce is correct.
Yeah.
Because it matches the hash, right? So whatever happened, now Bob knows that it happened fair and square.
Yeah.
By line 406. Right? If the Bob's random number is equal to Alice's number that she is now revealed, which we have authenticated as being correct, then guess who wins?
Yeah.
Not Bob.
Not me, yeah.
So now at this point we know that, we can go get the win script because, we're out of here. We're losing, so now we're only a winner. Bob can claim his winnings. Now what if Bob just decided to not have this line of code? Would this work?
Then they would, let's see, if Bob,
what if Bob just failed to? What if he refuses to admit that he lost? What if he fails to concede?
Well, she wins automatically. Yeah.
Then what now?
Alice will automatically win after the timeout.
Would she win after the timeout?
Or she can reclaim it, right?
Is this how the timeout works?
Bob wins. No, it's only for Bob.
So if Bob tried to claim the winnings,
it'd be a double spend, wouldn't it? Or
well, if Alice has claimed them already,
right,
and yes, it would be a double spend. You're right, but suppose for the sake of argument that Alice has not yet claimed her own winnings, that she only revealed the value to Bob that she won like a fool.
Without actually claiming.
But then the question is, could Bob still take the coins? Why or why not? He did not run this line of code with integrity. Could he still call?
No, he couldn't.
Why not? And we'll go here.
Because look at this Alice's number.
How is he gonna claim it?
Well, yeah, he needs Alice's signature, right? Because guess who else is checking this?
Well, Alice's code.
Script. Well, not Alice even.
The script.
The script, and therefore the miners.
Oh.
Your transaction will be rejected if you sign with an invalid signature. He cannot sign.
Oh, because it hasn't been passed to him, so he can't, yeah.
Yeah.
Because it'd be this stuff.
Not his right to sign.
Yeah.
He doesn't have Alice's private key.
Alice number, right? That's the one that would be hit.
Well, yeah, this is no question would run.
And then his signature wouldn't match with Alice.
No, of course it wouldn't match with Alice's other key, so he couldn't do it, right? So even if he didn't run this code, and even if Alice revealed it to like a fool, and even if she didn't claim it, and it wasn't a double spend,
that code does nothing. Yeah, that code does nothing as far as the contract's concerned.
No, it doesn't. It's just a way to nicely show a UI to Bob.
Yes.
But if he wants to be a sore loser and have his code throw errors, then down he can go into this area. All right, so let's compute a win script for Bob, right? How do we do this? It's similar to how Alice happens when she wins, right?
Yeah.
The SBTX is a new transaction. It's got an input from the acceptance transaction with output index 0. We've got a script which is the same as the output script which we created when we originally accepted the transaction. Sig hash type, none, anyone can pay, fork ID. We're computing a signature from the pre-image. And we've got the BSVTX, the hash type, input index 0. From the script, from when we originally created the acceptance output. Number of Satoshis is the challenge amount times 2 that Bob is claiming to win. SDK signature comes from Bob's key.
Yeah.
And the data being signed.
And that's the counterparty, yeah.
Right. Type coercion is here to be the correct value. Don't forget to set your SIG hash type. Transaction 2, don't forget to set your SIG hash type. Transaction 2, it is the output index of the new transaction.
Yeah.
Right? Or input index, rather, of the new transaction. And then we call, Alice is still revealing the winner, but guess who the winner is? It's not Alice.
No, it's Bob.
Alice was honorable. She did still reveal, but she didn't win.
Yeah.
This is just code that runs when Alice is being nice. Maybe Bob's UI would say, maybe we'll get to that later. But yeah, in this case, right, we call the function and Bob unlocks the coins, right? So that's used to compute the script, which is here. Now we have a script, right? Create action, redeem an input. Claim the winnings, right?
Yeah.
SPV data from the acceptance transaction. Outputs to redeem. Index 0, unlocking script from the win script. And you win a coin flip, right?
Right.
Return. What? You win.
You have to stipulate an output there or no?
Well, what happens to inputs when they come into the Metanet client and there's no outputs? If you unlock more coins than what you stipulate you want as output from your transaction in the Metanet client, how did that work in our ecosystem? We're so close to
doesn't it go back to your default or something?
Right, it does, because guess what? How generate change works. It goes back to your default.
Okay.
Good.
So if I have a transaction, right, and it gives me more money than what I originally had to begin with, I'll wait for this to load here. It increases your balance. Capture that as change. So we'll find one here that's green, if there is one. Looks like, and we'll update this.
Wait, is it in the default basket? Guess it would automatically go.
I guess these are all red because they're pretty cheap, but because I was doing a lot of testing here. But maybe there's one in which. But yes, the point is, if it's green, it's it's something that I don't know.
You have tempo.
There we go. Yeah, so I've got a one input of 1,000. I've only, it returns that much to my Metanet client balance. Because I didn't stipulate any outputs. It was only input that I stipulated.
Yeah.
That's how that works in the Metanet.
Right.
Creates that graph. Capture the rest. Right. Bob wins. Now, final boss of final boss. What if, so we win here, right?
Mm.
And we have this while loop, and this while loop breaks when the timeout expires.
Mm-hmm.
After a 5-second grace period for Alice to respond. So if we break out of here, now we know that we have an unresponsive opponent. Right?
Mm.
And Bob only can claim the winnings in this case. So Bob has this option in the contract. This option here. He needs to provide a signature only, and the time has to have passed.
Yep.
So, how do we make this happen? Well, we pretty much know the drill now, right? It's like, all right, how do you call a contract? So we make an instance of the contract, which is from the script from the output that we made when we wanted to accept the transaction. The contract, rather, right? Then we make a reclaim script, right? And we'll just cut to the bottom and we'll say, okay, well, create an action with the reclaim script. And here's what happens when you win a coin toss. We already know that part.
Yep.
The final thing is, how does this reclaim script get generated? And we've gone through this before, except for it's a little different. It's very slightly different. So the acceptance transaction is being redeemed from output index 0. Script is here. The number of Satoshis is the challenge amount multiplied by 2.
Sequence number, we haven't had that.
No, we haven't. That's different, isn't it?
And it's one less than max. To make sure that Alice can't do anything after this point.
No.
No?
That's not why. When does lock time matter? We talked about this earlier.
Yes.
I know it's been a long time.
Yes.
All right.
Lock
When
time.
does lock time matter?
If the sequence is not matched.
Yeah.
On at least one input, right?
Yeah, one input, yeah.
To disable lock time, right? Your transaction can be final when either your lock time is passed
Or your sequence is max.
or
Yeah.
your sequence
Yeah, that rhymes.
all of them. But if you want your lock time to matter, which in this case it has to matter, right? Why does it have to matter in this case? And I'll look at the contract here. We'll go easy on you guys because we're toward the end.
Yeah.
Why does the lock time have to matter?
Well, because of the timeout.
Yeah.
Right to have been expired.
Oh, yeah, because we haven't.
Bob
Yeah.
tries to reclaim it.
Right.
Yes.
If it didn't matter, then he could reclaim it any time, right?
Yes.
Therefore, a sequence number of one of the inputs has to be non-max if the lock time does matter.
Right.
That's why we have this line here.
Is it max by default?
Yes. If you don't
Yes.
set it, it's going to be max by default.
Yeah.
Lock time is disabled by default, and lock time is 0 by default. So even if this was here, if lock time was not set to be this, it would be 0. And 0 is not, as we're asserting here, 0 is not greater than the time lock on 106. So it wouldn't unlock, would it?
Nope.
So we've got that. We've got to set the lock time to some value greater than. We're just saying, plus 5. It could be plus 1. It's up here, right? We've got to set the lock time of the transaction there. Right? And that's important. We did that. Right? And then here's a thing that's a gotcha. I'll talk about this, and this will go into Hodlocker too. And then next time we'll talk about overlays after we review this, and we'll be done. Now anyone can pay fork ID, sign the pre-image. You sign with that, right? You sign with your transaction, with your input index, and your hash type, and your script, and your number of satoshis. All those things go into the pre-image. We're going to pound this into everyone's heads who goes through this course. This is what you sign the pre-image every single time.
Yeah.
SDK signature, create signature. Sign it, coerce the type, and then what?
Set the hash type.
Don't forget to set the hash type on your signature.
Yes.
Right, self.to. And you're saying, here's the transaction I'm spending to, and here's the input index of my spend. And then you're saying, well, Bob is going to win automatically after the delay, and here's the signature over that, which allows that to happen, right?
Right.
What's the gotcha in this create action call here? From line 508 all the way to line 524. What's the gotcha that I might have forgot?
Sequence number.
Yes,
Right?
sequence, yeah.
And of course, there's line 521 as well.
But where?
If
The challenge, yeah. Okay.
actually,
Oh.
if the transaction that you actually try to broadcast does not include the lock time and sequence that are equal to that which you signed,
Yeah.
Yeah,
then guess what doesn't match?
Yeah.
Going back to the pre-image here, right?
yeah,
Well, number 7
So-
doesn't match.
yeah.
Actually,
Well, number
three
9
is kind of
doesn't.
not going to match.
Yeah,
Because number 3 is wrong,
Yeah.
and number 9 is
Nine,
wrong. And
yeah.
your signature is not valid. So when you actually go to create the transaction using your standard wallet, you want to make sure that the
Yeah.
signature is
what's expected.
over
Yeah,
the correct thing, right?
yeah.
So that's how that works.
Mm.
You win a coin flip. Same thing, right? And then the last thing in this function is you return that you win. So congratulations, guys. Everybody who's gone this far,
Yes.
you win.
All right, where's my Bitcoin?
Yes.
I think we've gotten a long way. This has been a long time for those that aren't here in real time. If you're watching this recording, we recorded this over 2 days. But now we understand sCrypt at a basic level. This has been sCrypt 101.
Yeah.
Look forward to 102.
Yeah.
We talked about everything from sig hash to block time, sequence, stateful contracts, pre-images,
Yeah.
standard wallet, inputs, outputs, low-level Bitcoin script, stack operations, public keys, signatures, and everything in between.
Mm.
And how to deploy it on top of Babbage.
Yeah.
And
From the ground up.
from the ground up.
Just.
So congratulations on learning all of these things.
Mm.
There will be a test. The test is, what can you build with Bitcoin? How will you use this knowledge?
Mm.
And everybody in the world will be the one who is grading your test. Because now that you have this knowledge, how will you go forth and impact them by creating useful things?
Yeah.
If you impact them well, then maybe that will be a benefit. Not only to them, but to you, because you can set up the terms of how you want to benefit in the contract that they agree to when they use your systems. You can set up all those rules. Set up transaction fees for your own systems and platforms. You can do any number of different things using these technologies. And now you have the basic building blocks necessary to effectuate these outcomes and make these things happen.
Yeah.
I think that's about it.
I think so.
That's about it for the basic one.
Yeah.
We'll end it here.
Yes.